The topic is cryptography, and please give a really big round of applause for Ivan Vankov.
That's it. So, good morning, everyone. Thanks for joining me. And I actually have about 4 hours of information compressed into 30 minutes, 40 minutes, something like that. So I will speak quite fast. So as you may guess, we'll talk about cryptography. And in general, building a new type of cryptography is pretty hard. You must never attempt to do that. But using existing algorithms, using good practices are pretty easy, especially if you know fundamental rules and some basic ideas. And this is the goal of this lecture, to give you this fundamental understanding, to be aware how to use the cryptography and how not to use cryptography. So a couple of words about me. Thanks for the introduction. I'm Ivan Vankov, gatakka. Currently, I'm principal blockchain architect at Cognition Foundry. We are not doing ICOs and cryptocurrency shits. We are doing blockchain for real business. Also, I'm IBM champion. I have diverse background in security, machine learning, and as many of you, endless hours coding on different technologies, frameworks, whatever. So let's go back directly to the topic. So I will not give you a definition about cryptography because I respect your intelligence and your time. Everybody must know why cryptography exists and why it's useful. But I'm pretty sure that many of you are not familiar with the definition of secure. What makes one cryptographic algorithm secure? And the definition is pretty simple. Every piece of the algorithms used for encryption and decryption must be publicly known, must be available to everyone, no hidden information there. But without having the key that is used for encryption and decryption, nobody must be able to decrypt the message. This is the definition of secure. Let me show you a real example. Let's say that we want to encrypt the message free me. By the way, I'm not a visual guy, so you see from the style of the presentation that I'm a back-end developer and not a front-end. So let's say that we want to encrypt the message free me. So in general, the first thing that we have to do is to transfer it to bits and bytes, because in general, cryptography is working on a bit and byte level, and there is no difference between picture and text. So this is the bits representation of this text. The next thing that we have to do is to generate our key. And this key must be generated randomly and must be as random as possible. So this is our key. And here is the secret sauce. We do an XOR operation between the message and the key. If you are not familiar what is XOR, this is a pretty standard logical operator used in mathematics and computer science. I will not explain what it is. There is a bunch of information out there, so you can check it out. It's pretty simple. It's really well understood. So in green here, we have our encrypted message. That's all. That's how we encrypt. We take the message, we XOR it with the private key, and we have our message. So how we decrypt? We do the reverse. We take our encrypted message and we again XOR it with the private key that we use for encryption. And we have as a result our original message. And this is possible because XOR have this really interesting property. If you XOR something and then XOR it again, you go back to the original item. So I give you everything about this cryptographic algorithm, every piece of information, how you can encrypt and how you can decrypt. Do you think that you can crack that? Do you think that you can reverse, to understand what was the encrypted message? The answer is no. Even if you have all the computational power in the universe, you will not be able to decrypt this simple 6 or 7 letter message. Why is that? Because in the encrypted message itself, there is no information about the encryption process. So the only option that we have is to start generating random keys and XOR it with the original message. And there's not so many bits here. We can iterate all of them. And at some point, we will have our original message. In our case, it's free me. But by doing so, you will receive every other possible combination of letters and symbols. So you will have message like kill me, if you start me, or stuff like that. So all the messages that you will receive will be equally likely to be the original message. There is no information inside the encryption message how you can decrypt it. So without any additional information that is outside of the cryptography, all the messages look the same. And this is the definition of secure. And this particular algorithm, this is perfectly valid cryptographic algorithm, this is a definition of perfect cryptography, something that is completely unbreakable, because you have no idea what was the original message. You always have to use open cryptographic algorithms, well established, tested, and by doing so, you are sure that the weakest point, the only thing that you have to protect is your private key, the key that is used for encryption, not the implementation, not the algorithm. You always must use open algorithms. So this is perfect cryptography. Let's start using it. End of the lecture, right? Not exactly, because perfect not always mean practical. And there are a couple of problems with this algorithm. And the first one is key size. As you may guess, the key size must be equal or greater in length with the message. So if we want to encrypt 1 terabyte of data, we need 1 terabyte of key, which is unpractical. We have to store this key, we have to distribute this key. It's absolutely unpractical. The second problem is not so obvious, but it's key reuse. In this particular algorithm, you must never use the same key more than once. If you have 2 or more messages that are encrypted with the same key, it's trivial to find the key using just a pencil and a sheet of paper. It's so easy. So you must never use the key. And for that reason, this particular algorithm is called one-time path. The name implies that you must never reuse the key. Again, this is really unpractical. But wait, there is more. We need a message authentication. In the current implementation, there is no way for the receiver to be sure that this message was not altered in some way. Imagine that some bits are flipped during transmit, network error, disk error, or somebody intentionally do that. So this is also a huge problem. But we need a digital signature to be sure who was the author of this message, who was the creator of this message. So digital signatures, in some cases, are not necessary, but digital signatures are the foundation of security in internet. And without them, the internet just cannot work. So, and the last one, and the hardest one, is the key exchange. So let's say I want to send you an encrypted message, but you need the key to be able to decrypt it. So how I will send you the keys? If I send them openly, somebody can steal them. We must have some secure way to exchange the keys. But if we have secure way to exchange the keys, why we not use this secure way to exchange the message directly? So it's something like a chicken egg problem. To have a secure communication, you need the private keys. But to have the private keys, you need a secure communication. And actually solving this problem was the biggest breakthrough in cryptography ever. So these 5 problems define the modern cryptography. Luckily for us, all of them are solved using different techniques. And actually in the next couple of minutes, I will explain you how each one of them is solved and how you can use them, etc., etc. So before we go one by one, let me introduce a little bit of terminology. Currently, the cryptography is split in 2 main branches: symmetric cryptography and asymmetric cryptography, also called public key cryptography. And the difference is pretty simple. In symmetric cryptography, use the same key for encryption and decryption. In public key cryptography, use different keys for different operations. Later on, it will be much clearer for you what actually is going on. So let's say that you want to encrypt something. You want to encrypt your home folder in a secure way. So the first thing that you have to choose is the algorithm for encryption. And there are a bunch of them. I mean, there are so many of them. But the good thing is you have one choice that is working in, let's say, 99% of the time. And this thing is called AES, Advanced Encryption Standard. It's a symmetric encryption, so you use the same key for encryption and decryption. It's one of the most used and most tested, and most importantly, CPU accelerated. All modern CPU have special hardware instructions inside that makes encryption and decryption really, really fast. And also, it's a standard, not implementation. So IS implementation on Raspberry Pi will be completely compatible with IS implementation of, let's say, IBM mainframe or something else. So everything can talk with everything, can encrypt and decrypt. And also, it's extremely flexible. So how IS address these 5 problems? So let's start with the second one. And this is the key reuse. So in general, IES is designed so you can use the same key as much as you want, even for the same messages, etc., etc. Why so? I mean, it's out of the scope of this lecture to explain you because we have to go really deeply into mathematics of IES, rounds and stuff like that. All the standard is public, all the implementations are public, so you can go deep if you want. But you have to know that in IES, you can generate your key and you can use it as much as you want. So this problem is solved using clever mathematics. IES have 3 security levels: IES 128, 192, and 256. The higher the number, more secure is the encryption, and also it requires much more CPU time. And actually, this number represents the number of bits of your key. So if you're using IES 128, your key must be exactly 128 bits, not bytes, bits. And no less, no more. And so here is the interesting question. Okay, let's say you want to encrypt 1 gigabyte of data, but your key is always 128. There is no difference between 1 kilobyte and 1 gigabyte. So how you can encrypt something so big with something so small? And here is the most confusing part for most of the people that are starting with IES. Cipher modes. IES have different cipher modes, and the idea of the cipher mode is exactly that. How you can encrypt so much data with such a small key. And these are officially supported cipher modes in IES, and they work differently. They have different parameters, they have different security levels, they have different behavior. Some of them are really, really specialized. So you must know what each of them is doing. But actually, it's not so complicated. Let me give you an example, which will be much more clear for you. Let's take ECB. So ECB, in general, is taking the data, split it into blocks of 16 bytes, and then encrypt every single block individually with the same key. And because IES allows us to reuse the key, I mean, all the blocks are encrypted, then combined in one message, and that's your thing. That's good. That's pretty simple. That's really efficient. It can run in parallel, etc., etc. But there is a big problem with ECB mode. And the problem is that it encrypts the data, but not the patterns. You must never use this mode in IES. Absolutely never. Just don't do it. And let me show you why. Let's say that we want to encrypt this message. And this is the result. So the colors are different, but the pattern exists. So if this was a text instead, using simple statistical analysis over character frequency, a lot of information will be revealed. So never use ECB. So what to use then? There is something called CBC, and this is general purpose cipher mode. That is working similarly to ECB, but the first block is encrypted, then the second block is XORed with the first one, then encrypted. Then the third block is XORed with the second one, and then encrypted, and so on until the end. And because the blocks are connected, actually, all the messages are, the message is different. And actually, here is the result. This is the same picture using the same key, the same implementation, just the mode is different. So it's pretty important to choose your proper encryption mode. And as I mentioned, in most of the time, CBC is what you need. Some of them are really special, for example, for hard drive encryption and stuff like that. If you need something special, I mean, you start looking for that, and actually you will find it. But we have a couple of problems with CBC. And not only with CBC, but most of the mods. If you encrypt the same message with the same key, you will have the same result. And also, the first block is not XORed with nothing, so it will be always the same. And see, this is a huge problem in cryptography. In general, everything that is predictable, repeatable, or have some patterns inside the cryptography is a bad thing. See, you have to understand that any attack on our modern cryptographic system is not by finding some crazy mathematical way to break it, like solving the elliptic discrete logarithmic problem. Instead, the attacker will collect as much as data as possible and start looking for different type of patterns and stuff like that, and then combining all this information, a really serious attack can be executed. I'll give you a simple example. Imagine that you encrypt your data for your login page, and somebody is entering his username and password, and this data is encrypted. If the message is always the same, the attacker can see that this message is exactly the same as the previous one. I mean, the attacker will not see the actual username and password, but because the encryption message is the same, he can relate it to this particular user or to this particular user. This is really, really bad. I mean, this is a simple example. There are more complicated ones, but I'm pretty sure that you start to get the idea. So how this problem is solved? It's pretty simple. There is something called EV, initialization vector. It's not Roman 4, it's initialization vector. So it is just a bunch of random bytes, completely random bytes. And they are provided to the function, actually, that will do the encryption. And this EV will be used to XOR the first block. And because all the blocks are connected, when you change the first block, you actually change all of them. And because EV is random, the message will be completely random. So what are the characteristics of IV? So it's not necessary to be secure. I mean, you don't have to encrypt it or stuff like that. But the most important thing about EV is that it must be random and unpredictable. This is the trickiest part. And you must generate completely new IV every time that you're doing encryption. Doesn't matter, are you using the same key, the same message. When you do encryption using IES CBC, you always generate completely random EV. And the recommended size of this is 16 bytes, not bits, bytes. And actually, to be able to decrypt the message, you also need this information, this IV. So the general way how this is done is you encrypt your message, and you just take these 16 bytes and put it in front of the message. Just prepend the message, and you send this message to anyone. If the attacker have access to this IV, this will not help him in any way actually to decrypt the message or to predict anything. So this is the normal way how it's done. You encrypt, you take the IV, put it in front, send the message if you want to decrypt, remove the first 16 bytes, this is your IV, you provide the message and the IV and you decrypt the message. So actually, it's not so complicated. And also we have some small problem with CBC. What will happen if the data is not multiple of 16 bytes? Because, as I mentioned, the data is split to blocks of 16 bytes. Depending on the implementation, nothing bad can happen or something terrible can happen. So you must always be sure that your message is multiple of 16 bytes. And if it's not, just put a random bytes at the end or zeros or whatever you want, just make it equal to 16 bytes. And there's a lot of scheme about padding. One of the simplest one is you put 1 byte in front. That will tell you how many bytes are at the end are for padding. And for example, when you decrypt your message, you read the first byte. If the number is 5, that means you have to remove the 5 bytes from the end, and of course the original one. I mean, this is just an example. You have thousands of ways actually to do the padding. So as you can see, it's not so hard. If you follow these simple rules, use CBC, use random keys, use different IV for every message, and you put your message to 16 bytes, you can be pretty sure that you're following the best practices, and you actually will be quite convenient that this is not breakable. So until now, I just solved the 2 of the problems, key reuse and the key size. So let's go to the message authentication code. As I mentioned, there is no way for the receiver to be sure that this message is not altered in some way. So the naive approach of fixing this is to create some checksum of the message or hash of the message, append it to the end or stuff like that. But this will not work, because if an attacker is able to switch some of the bytes, what will prevent him to switch the bytes of the message and recalculate the hash or the checksum again? So something more advanced is needed. Something that includes the private key, because the attacker don't have access to the private key. So again, the naive approach will be to use the private key as a salt. You just take the private key, append it to the message, and make some cryptographic hash. Don't do that, please. Never do that. There is a real chance that you will leak your private key. So for that reason, there are a lot of algorithms that are doing exactly this. They take the message, they take the private key, and give you a couple of bytes, similar to hash. But it's done in a really secure way. It's unpredictable, so if the attacker changes some of the bits, it's not able to recalculate the hash. And it's pretty efficient, etc., etc. And as I mentioned, there are a bunch of those algorithms, but luckily for us, in the standard of IS, there is something called IS-GCM. And it works in a similar way as CBC. So you provide your message, you provide your key, you provide your initialization vector, but GCM will encrypt the message, will fix the padding of the message, and will set this message authentication code. And when you decrypt using IS-GCM, the message code will be verified, and if there is some mismatch there, the decryption will fail, and you'll be pretty sure that something wrong has happened. And the most interesting part here is that you don't take care about the padding. So if you need good encryption that is having message authentication code, IS-GCM is the way to go, and also some of the Intel processors also have a specific optimization about this system. So it's pretty damn good. So until now, I think things looking quite simply. I'm pretty sure that you understand them. But let's address the random numbers, because this is the most misunderstood and misused part of the cryptography. So as you may know, all the modern computers that are Turing complete and are based on von Neumann architecture are absolutely incapable to generate random numbers. It's not possible. For that reason, there is something called PRNG, pseudo-random number generator. You must never, absolutely never, without any exception, use PRNG for generating private keys or initialization vectors, because they are predictable, absolutely predictable. And after the lecture, I can tell you a story how about 100,000 Bitcoins were stolen because some idiots use PRNG. And for what you have to use is proper cryptographic random number generator, and every modern operating system have one. And actually how they work is pretty fascinating. Some of the companies are collecting noise of the streets, some of the other companies are using lava lamps, stuff like that, or some quantum computer bullshits. So this is how 3 of the problems are solved: key reuse, key size and message authentication, and also the random numbers. But the last one, digital signatures and key exchange, cannot be solved efficiently using symmetric cryptography. We have to use asymmetric cryptography or public key cryptography. So what actually is public key cryptography? Right now, we have two main algorithms. One is called RSA, and the new one, it's called elliptic curve. And in general, in this type of cryptography, you have two keys, private key and a public key. So you have to keep your private key as private and as secret as possible. But the public key can be shared. You can put it in your website, in Twitter, you can print it on your t-shirt, doesn't matter. It's designed to be public. So the public key is generated from the private key in a really efficient way, but there is no easy way to find the private key from the public key. So it's a one-way function, similar to hash. It's really easy to calculate the hash, but it's really difficult to understand what was the original information. And you have to understand that the same private key will always generate the same public key. So for what we can use public key cryptography? So we can use it for three things. Can be used for data encryption, but please note this red star. I will explain why it's there. Can be used for digital signatures and can be used for key exchange. So as you can see, it's much more versatile than the symmetric cryptography because we can do a lot of stuff. So in this small table, I'm showing what can be done in which key. If we want to encrypt, we encrypt with the public key, but this message that is encrypted with the public key can be decrypted only with the private key. So if I put my public key on my website and you want to send me a secret message, you take my public key, you encrypt the message, you send it to me, and I'm the only person that is able to decrypt it because I'm the only person that keeps the private key. But please notice again the stars there. They're really important. So about the signature, you can create the digital signature using the private key, and this digital signature can be verified using the public key. So if I, let's say, create some application or PDF file or something like that, I sign it with my private key, and you can verify it using my public key. And also, these keys can be used for key exchange. So let's go a little bit more details about the different algorithms. So about RSA. RSA have a couple of versions. And actually, this number represents the number of bits for your private key. 1,000, 2,000, 3,000, etc., etc. So anything below 2048 is considered weak. So 2048 is the recommended size. If you require more security, I mean you have to go to 3072 or more, it's better to use elliptic curve because the required CPU is growing exponentially compared to the size of the key. So it's not efficient. Elliptic curves are much more efficient. So if you must use RSA, in any case, 2048 or 3072 are the preferred one. Above that, I mean, you will struggle. I mean, your CPU will have huge problems. So about the elliptic curves. In general, in elliptic curves, you don't choose the key size. You choose the elliptic curve itself. And there are infinitely many elliptic curves, and most of them are pretty terrible for encryption and decryption. But there are some special ones, and they have special names, like X25519, curve P256, etc. So these three curves that I'm showing here are well established, well used, and the first two are the most used in TLS, in web, in browsers. The browsers understand them and they use it for key exchange, for cryptography, etc., etc. The latest one, SecP 256K, no, this is the Bitcoin and Ethereum and all cryptocurrency curve. It's not supported by the browsers and by many applications, but because blockchain is everywhere, I mean, at least in media, it's good to know that you can use it, but be aware that the encryptor and decryptor must use the same curve to be able to encrypt and decrypt the message. And see, probably some of you start wondering, okay, IES we have 128, in RSA we have something like 3,000, here again we have 255, 56 bits. Why there is so much difference between them? So, because they are different algorithms, and this table shows you the relative size in security. So, for example, IES 128 will give you the same security as RSA 3072 or elliptic curve that is 256. So, as you can see, RSA is pretty inefficient in creating a good security, and there's really serious reasons why that. Why is that? And as you can see, IES is the most secure one, and elliptic curves are really, really good. So how you actually generate this key? It's pretty simple. You generate a random number, and that's your private key, and you keep it private. Then you apply a really specific mathematical operation over this private key, and the result of this operation is your public key, and again, you can share it. So, in RSA, not all numbers can be used as a private key. Actually, the numbers must have some really specific properties, like to be a prime numbers, etc., etc. Actually, to generate a proper private key for RSA is a challenge by itself. So that's why RSA's key size is so big, because not all the numbers are good for encryption. In IES or in elliptic curve, any number, except 0, of course, is good private key, and you can use it. So this is just general understanding about the cryptography, so about the public key cryptography. So let's talk a little bit about the digital signatures. As I mentioned, digital signatures allow us to sign a document or application or message or file, doesn't matter, and to allow any other person to verify that I was the person that signed this message. And also, as added value, is that this digital signature is also working as a MAC. So in MAC, you just verify that the message is not altered, the message integrity. In digital signature, you also verify that the message is not altered, but also there is information who was the author of this message. And because the situation is pretty simple. When I sign something with my private key, somebody can verify it with the public key. But because the public key was generated from the private key and the signature was generated from this private key, I mean, if the verification passes, that's pretty sure that the owner of this private key was the person that generated the signature. And this signature is just something like a hash, around 256 bits, depending on the algorithm and key size, etc., etc. So it's not so big, but you have to take some space for it if you're doing some protocol for exchange. And later on, I will explain you why digital signatures are so fundamentally important about the internet. But let's go to the other thing, this star that I show you about the encryption. Public key is not used for encryption in practice. And the reasons, there are many reasons about that, but the first most important one is that you can encrypt only data that is around the size of the key. So if you're using 256 bits elliptic curve, you can encrypt no more than 256 bits. It's really slow, it's extremely inefficient. You cannot encrypt in an efficient, proper way, let's say 1 megabyte of data. And the other reason why it's not so used is, actually, it's not a technical, it's a logistical one. So let me explain you. The cryptographers are really practical guys. So we have something that is working. Let's say IES or CHA-20, this type of algorithms, they're really efficient, they're well adopted, they're hardware accelerated, etc., etc. So why you have to invest in another algorithm while if you solve the problem of exchanging the keys, then you can use this symmetric cryptography. So if there is a way to exchange the key in a secure way, then why to invent a completely new algorithm and to wait decades actually to be verified, certified, implemented, etc., etc. So in general, using RSA or elliptic curve, you cannot encrypt data in a similar way as IES. It is used in things like Diffie-Hellman or TLS. It's used, but it's encrypt a really small piece of data. So when I mentioned Diffie-Hellman key exchange, actually this is the way how this problem is solved, how we can exchange key. And actually, this was the biggest breakthrough, as I mentioned. And the guys that actually found that are Diffie and Hellman, and they created this protocol. So Diffie-Hellman allows you to exchange keys between multiple parties. Normally are 2, but nothing prevents you to be 20 if you want. It's based on public key cryptography, and actually the mathematics behind is completely different for RSA and elliptic curve because these two algorithms are absolutely they have nothing in common. RSA relies on prime number factorization, elliptic curve is using elliptic curves over finite fields, etc., etc. So there is something called ECDH, elliptic curve Diffie-Hellman. So what is happening here? So let's say we have Alice and Bob. In general, in cryptography, always we use Alice and Bob. Nobody's sure why, but it sticks like as a culture. So what's happening? Alice gets Bob's public key. Then Alice multiply her private key with Bob's public key. So let's say my private key with your public key. I just multiply them. In the other hand, you take my public key and you multiply it with my with your private key. Sorry, your sorry. Okay, my private key with your public key and my public key with your private key. And because the way how elliptic curves are working, both of us will have the same result. We will have the same number. But see, in the network, the only thing that is transmitted are our public keys. They're public. I mean, they're designed to be public. So if somebody is sniffing the traffic, the only thing that we will have is our public keys. But without having the private keys, there is no way actually to generate this common secret. And when we achieve this common secret, then we start using IES. And we use this common secret as symmetric key because IES is much more faster, much more secure, much more efficient, it's hardware accelerated, tested, etc., etc., etc. So this is the main idea. I mean, the mathematics is much more complicated. I'll give you the general understanding what is happening there. But if you want more details, just look for Diffie-Hellman, key exchange, and this. I mean, there's a bunch of information about that. So, and this is the common way that is used in, what's happening, what's happened? There's the common way of exchanging in TLS 1.2 and also in 1.3. Let's say the client is the browser and the server. The client say, okay, I want to speak TLS. Here are the ciphers that I'm supporting. The server is saying, okay, I want to use this thing. Here is my key share. The client responds back, okay, this is my key share. This is more complicated. In TLS is much more complicated than that because a lot of randomness is added, etc., etc. But after these key shares are exchanged, then all the communication between the browser and the server is encrypted using IES or ChaCha20 or something like that. But there is a problem here. Imagine this scenario. Your browser, your server. The browser is sending a request and some hacker intercepts this message and present himself as the server. So the key exchange happened between the browser and the hacker. In the meantime, the hacker represents itself to the server as a client. So he's doing a key exchange with the server. So the browser is thinking that it's talking to the server, but actually is talking to the hacker, and the server is thinking that it's talking to the client, but actually is talking to the hacker. So the hacker will have access to all the communication, and not only read the communication unencrypted, he also can alter the information or send completely new messages. This is called middleman attack, and it's one of the worst things that can happen. So how this can be prevented? There is something called X509, or digital certificate or SSL certificate for you guys that actually are doing web servers and stuff like that. So digital certificate is something that holds additional information. It holds the public key, but it holds, let's say, the domain, the name of the company, location, and a bunch of other attributes. So who can create these certificates? Anyone. I mean, I can create this certificate by my own, and I can say I'm owning the servers of Google or Facebook and stuff like that. If I'm generating certificate by myself, it's called self-signed certificate, and from security point of view, it's worthless. Absolutely worthless. It's good for development and testing and stuff like that, but in general, for security, it's worthless. To become a proper certificate, we have to do a digital signature or certificate signature. So how this is happening? First thing that you do is you generate your public and private key using RSA or elliptic curve. Doesn't matter, it's work the same. Then you create something called CSR, Certificate Signing Request. And actually, this is just a text file that holds your public key and your claims that you are owning, let's say, google.com, your this organization, etc., etc. And then you send this CSR to Certificate Authority, or CA in short. And this Certificate Authority will look your claim in the CSR and will do investigation. They may call you, they may require your ID, they may require some documents, they may require to put something in your server. Depending on the security level, jurisdiction, and stuff like that, this procedure can be completely different. But the idea of the CA is to verify that your claim is correct, that you are this person, that you are this organization, that you own this server, etc., etc. And if this is okay, then the CA will issue a certificate holding this data. I mean, your, let's say, domain name, organization, and also will include the digital signature of the CA. That's the tricky part here. This is the most important part. The CA will sign this certificate. And if we look, this is example for Wikipedia, we can see that this certificate is for Wikipedia and is signed by DigiCert. There are many companies that are doing this. It will expire on 24th of January next year. We have the fingerprints, the serial number, and a lot of other information. And how actually this will solve this middleman attack problem? It's pretty simple. When the browser starts talking with the server and say, okay, I want to speak TLS, the server will respond something, and the browser will ask, give me your certificate. I want to see your certificate. So if the hacker is in the middle, he can return some self-signed certificate, but the browser will it's really easy to see that this is a self-signed certificate and will reject the connection. Or if the hacker is trying to do something clever, the verification of the signature will not be okay, because digital signatures are really hard to fake. It's really hard. So the only way that the hacker can present a proper certificate to the browser is if somehow he is able to generate a fake certificate from the certificate authority. And in general, this is not happening because CIs are, they're pretty responsible about that. In general, their private keys that are used for sign are stored in the places where they first shoot you, and if you survive, then we will ask you what you're doing there. And I'm not exaggerating here. There is a story about one data center in Panama. One paramilitary organization wants to get inside. They spent more than 2 days using explosive and hard machinery just to be able to enter inside the data center. So it's pretty serious. So the digital signature, when the CA actually put its digital signature, it's guaranteed that this information in the signature is okay. And if the hacker tries to get the proper certificate, it will be rejected. And he cannot fake this certificate. But here is the interesting question. How the browser will know, how to check the signature? It needs the public key to verify the signature. And for that reason, every operating system, as part of their system updates, they provide a list of all verified, certified certificate authorities in the world, their public keys. And when a browser actually receives the response from the server, it starts looking for this digital signature and starts verifying all the public keys that are inside the OS and make a verification. If the browser finds, or the OS finds a match that this public key verified the signature, the browser directly assumes that this is a proper certificate. Again, it will verify the domain name inside the certificate and a lot of other stuff, but the main part is that the browser will verify the digital signature. And there is one tricky way, actually, how you can cheat this system. If the hacker somehow is able to inject in your operating system a public key and register it as legitimate one, then he can use the private key that was used to generate this public key to sign its own certificate. And there is no way for the browser and the OS to understand that this is a fake certificate, because everything relies on that. The public key is provided by the OS vendor, and if the verification is successful, then this is a proper certificate. OSs are trying to do their best, actually, to prevent this type of attacks, actually, how you can inject this certificate. But let's say it like that. If you're an idiot, there is no technology that will prevent you. Be really careful when some application or stuff like that are willing to inject a certificate or to register a certificate in your OS. Because you can go in this situation and there is no prevention. So, don't be idiots. If you don't understand something, ask. Good practices in cryptography are established. Nothing is secret there. Everything is publicly available. There are a bunch of people that will help you, and just ask. Don't be idiots. Thank you.